Welcome to the last video on aldehydes and ketones. So next we should talk about carbon nucleophiles. So when we have a carbon nucleophile, then we are actually adding carbons to our molecule. The first example is the Grignard reagent, which you'll recall from a previous chapter that we just add the Mg to an alkyl halide, and then we end up being able to make that carbon as a nucleophile. So in this case right here, we have a Grignard that takes the CH3 and it's a CH3 minus. That's our nucleophile, and it's going to attach to the carbonyl. And in the second step, we'll protonate, giving us the alcohol. Same here. So it works with an aldehyde and a ketone. Negative CH3 here attacks the carbonyl, kicks up, we protonate, and now we have an alcohol. Something that you want to keep in mind here is that when we have a carbonyl, ketone, or aldehyde, it can attack from either face of the compound. So the nucleophile can attack from either side, giving us a racemic mixture when we're done. So the mechanism for this reaction, here's our negative carbon attacking the carbonyl, kicking up, giving us our tetrahedral intermediate, which is an alkoxy anion. And then in the second separate step, we're going to add water and we're going to protonate that oxygen, bringing us back to the alcohol. So if we have a ketone and we undergo Grignard reagent, we'll end up with a tertiary alcohol. Cyanohydrin is the next reaction we're going to talk about. And in this case, we have HCN added. So C and the CN here is going to be our nucleophile. So that carbon attacks the carbonyl, kicks up, and then protonate in a second step. This reaction works best under basic conditions. So as long as we have a catalytic amount of base, we should be fine. The mechanism for this reaction, you'll see, is getting a little redundant, but here's our nucleophile attacking the carbonyl, kicking up, tetrahedral intermediate gets protonated. And so then we end up with our final product here, which is a cyanohydrin. The acid workup is not necessary since HCN serves as a source of protons as well. To achieve basic conditions, we'll add KCN in with the HCN so that we can have some of the CN minus around. And we have a little bit more of that around than we do the protonated version. And so then that's going to give us the base conditions that we need. In this reaction, we should note too that a new chiral center is formed. Once we have that cyanohydrin, we can actually take that a step further and reduce it with lithium aluminum hydride, and we convert that C triple bond N into an NH2. And of course, that's going to be racemic, and that's going to give us our primary amine. We can also react that cyanohydrin with acid and heat, and it's going to take the cyanohydrin, right, that C triple bond N, and convert it into a carboxylic acid. So these two reactions might be helpful as we just kind of put them into our pocket in order to potentially use them in synthesis problems. The next reaction I want to talk about is a Wittig reaction. And so what happens with the Wittig is that we increase the carbon skeleton. And so here's how that reaction happens. So here's our aldehyde or ketone. With the Wittig reaction, we use the yllid. In just a second, we'll learn more about it. This carbon phosphorus bond is even more than a dipole. So we have a negative charge on the carbon, positive on the phosphorus. And so then this is going to be our nucleophile right here. We'll see how the reaction progresses, but ultimately it takes a ketone or aldehyde and brings it to a carbon-carbon double bond. So not only have we added a carbon to our molecule, but we've added a carbon-carbon double bond. So here's just another example shown here. So this is the Wittig reaction. Takes a carbonyl and converts it to a carbon-carbon double bond. So this species that we need in order for the Wittig reaction to happen is called a yllid. It's called a phosphorus yllid to be specific. And that phosphorus group is going to be what makes this carbon negative, which makes this carbon possible for us to have a reaction. And if you think about it, it's really just the resonance structure of this species right here. So the yllid is a neutral compound that contains a negatively charged atom adjacent to a positively charged heteroatom. The mechanism is likely a 2+2 cycloaddition between the Wittig reagent and the carbonyl, something like this potentially. So we have our carbonyl next to the phosphorus yllid, where the negative carbon aligns with the partial positive carbon of the carbonyl, and the positive phosphorus aligns nicely with the oxygen. We have this oxophosphatane intermediate, where we have this four-membered ring that then rearranges to push the double bond in between the carbon and the carbon here, giving us the double bonded oxygen to our phosphorus. The fact that we are also forming this very stable triphenylphosphine oxide byproduct helps drive the equilibrium to favor the formation of the alkene. So creating the Wittig reaction is a two-step reaction, starting with the alkyl halide shown here. The first step is an SN2 type reaction with the phosphate attacking the carbon, kicking out the bromine. And in the second step, we have N-butyllithium acting as a strong base, deprotonating that carbon, giving us our phosphorus yelid. Here are the two resonance structures. So the Wittig reaction is pretty cool because it gives us this new carbon-carbon double bond. I think it's the only example of common organic reactions that do this for us. And the Wittig reaction is stereoselective. So it turns out when you're using the Wittig, depending on what alkyl halide you start with, the Z alkene is favored. If the Wittig reagent contains an electron withdrawing group, however, we can push it towards the E alkene as the major product. For example, here's our yelid, and if we have this electron withdrawing group, the ester group here, the carbonyl with the OR group, that ester is going to be electron withdrawing, and so it's going to force the reaction to happen E. And the last reaction that we're going to learn in this chapter is called the Baeyer-Villiger oxidation. And so in this case, an oxygen is inserted into the aldehyde or ketone between the carbonyl group and the neighboring carbon. And in this case, we're going to use the peroxy acid to pull that off. So we have an aldehyde or ketone, we're going to use peroxy acid, and then we end up creating this ester product. So the mechanism for this reaction, the nucleophile for the nucleophilic attack here is that second oxygen in the peroxy acid, that one that's protonated at the end. So that's going to attack the carbon, kick up. Here's our tetrahedral intermediate. We're going to have an internal proton transfer, and then that's going to make this a good leaving group. So what happens is the oxygen kicks down to reform that double bond, and then this R group hops over onto the oxygen, and then this group leaves because this is a good leaving group. And we end up with our ester and then that leaving group, which is a carboxylic acid. And that there is called a rearrangement because this step right here is a little bit weird when I said that R hops over. So it's rearranging, kind of like we had methyl shift or hydride shift. This is going to be an alkyl shift. So a cyclic ketone produces what's called a lactone. And so there's the cyclic ether. For an aldehyde or unsymmetrical ketone, the rate of migration is as follows. The most likely to migrate is a hydrogen, followed by tertiary. Secondary and phenyl are about equivalent, then primary and methyl. This trend helps us determine regioselectivity. So in other words, which side of the ketone is the oxygen going to insert. So if we use this trend here, let's try to determine which side the oxygen is going to go on. And so tertiary and secondary and phenyl are better than primary and methyl. So this is a methyl. And so it's going to insert on this side for sure, right? Methyl versus secondary. And then down here though, however, right, hydrogen is the most reactive. And so then we're going to have it insert here, which then gives us the carboxylic acid rather than the ester. So if we kind of try to summarize this whole thing in terms of synthetic strategies, which is probably going to be an important part of both the knowledge check and of the quiz, and then potentially then on the final exam as well, let's think about two questions we can ask as we're starting to figure out how to design a synthesis. And the first thing that we want to ask is there a change in the number of carbons in the skeleton? And if there is, then we can really focus on these three reactions probably being involved: the Grignard, the cyanohydrin, and the Wittig. So one of these three reactions inserts a new carbon into the skeleton. And so that's going to be important when we're considering how to start with that retrosynthetic analysis of the synthesis problem. And then the second question, is there a change in functional group? So we know a lot of reactions that can help us change functional groups. Here's a quick summary of the chapter and all the reactions that we've learned this chapter and previous, right? And so just kind of give you an idea of what we might be thinking about in terms of synthesis problems. Here's a review of the reactions, and I will have this available in Brightspace separately as a document that you can just refer to. But this is literally a summary of everything that we talked about in this chapter, and it's a nice way to kind of keep track all the reactions that you have learned in this chapter and need to kind of keep track of in terms of both the quiz and in terms of synthesis problems. There you have it, ketones and aldehydes, how to make them and how to use them. Good luck.